Hi, Dr. P here, and in today's lecture, we'll start off with a little bit of an introduction to organic chemistry, um, and also take a look at a review of atomic structure. So let's go ahead. Chapter 1, lecture 1. So we'll look at an intro to organic chem. We'll do what should be a review from Chem 1A. Oops, sorry, atomic structure. Let's review. And then I don't want to make this video too long. I'll put it in the next video, but we'll start talking about chemical bonds. All right. So let's start off with the question, what is organic chemistry? Now, many of you, when you hear the word organic, probably think of, say, organic produce that you find in the supermarket. Well, that is a definition of organic, but it's not one that chemists use. So originally, the original definition was that organic compounds come from living things. And by original, I mean this is, like around 1806. But then in the early 1800s, around 1826, urea was synthesized. In particular, it was synthesized from ammonium cyanate. So ammonium cyanate has the following formula here. And this delta indicates we are heating things up. And we end up getting, I'm going to use some bond line formula, which is a particular way of representing chemical structures. But this is our ammonium cyanate. And by heating it, chemists were able to make urea. Now, ammonium cyanate was considered inorganic, and urea is considered organic. Urea is an important biological molecule, and it's an intermediate in certain protein metabolism, the synthesis of amino acids. We call it the urea cycle. There's a part where urea plays a large role. It's excreted. Mammals excrete nitrogen in the form of urea in urine. Now, ammonium cyanate was inorganic, but urea is organic. So clearly this old definition of organic compounds come from living things doesn't work because we've made urea from something inorganic. So the modern definition The modern definition is organic compounds are carbon-containing compounds. And that's usually with hydrogen. And I'll use abbreviations typically when I write notes on the board or on a paper like this. So my W/ here is with. Some exceptions. Carbon dioxide, the carbonate. Sorry about that. I was doing bicarbonate. Bicarbonate's also inorganic. So CO2 and CO3, 2-, are inorganic. Okay, so just to give you guys an idea of where we're coming from. All right. Now, of course, I will scan in these notes and they will be posted so you can refer to them while you're watching the lecture video. All right, well, let's take a look then at a little review of atomic structure. And again, you guys should have seen this in Chem 1A. Now, in an atom, we have at the very center, we have our nucleus. And then surrounding that is our electron cloud. So I'll abbreviate electron with an E and a minus sign. Now, the nucleus is small, several orders of magnitude smaller than the radius of the atom. It's heavy. Particles that make up the nucleus, protons and neutrons, are roughly 2,000 times more massive than electrons. So a proton's about 2,000 times heavier than an electron. And then, of course, the nucleus is positively charged. And it's composed of protons, which I will label as P+, and neutrons, N0. Now, contrast that with our cloud of electrons, which are light, that is not heavy, and they're negatively charged. One thing to note here is that this dotted line represents our it's essentially it's the size of the cloud of electrons. We could say that there's a 95% chance of finding the electron there, or um, 95% electron density. That's another way of phrasing it. Because remember, electrons are they're so small that they have both particle properties and wave properties. So looking at them like a particle, we would say there's a 95% chance of finding the electron within this radius. Or we can say that 95% of the electron wave density is within this radius. So that's our atom. We can take a look at way that we represent atoms sort of in general. So if we have some atom X, so X is going to be our atomic symbol. We would write a superscript A in front of the X to indicate the mass number. And I'll abbreviate number with the pound sign there. So that's the number of protons plus the number of neutrons. That's our mass number. With the subscript here, so superscript A is the mass number. Subscript Z here is the atomic number. Which is simply the number of protons. And then we can have a superscript after our atomic symbol that has the charge. Here I'm going to call it Q. And the charge is the number of protons minus the number of electrons. So if we have fewer electrons than protons, we have a positive charge. More electrons than protons, we have a negative charge. So for example, we could have carbon 12. And, you know, I think of the atomic number sometimes as a bit of, well, it's kind of from the Department of Redundancy department, in that it tells you the same thing that the atomic symbol does. So the atomic number and atomic symbol both basically tell you the same thing. Mass number will tell you something interesting because the atomic number gives you protons. So mass number minus atomic number is your number of neutrons. So our protons give us our element identity. That is what element, what type of element the atom is. Our neutrons are going to give us isotopes. For example, carbon 12, carbon 13, carbon 14 are all isotopes. They all have 6 protons, but they have different numbers of neutrons, 6, 7, and 8 in this case. And lastly, our electrons, they're going to give us our chemical reactivity. And specifically, it's the valence electrons that will give the chemical reactivity. All right. So to sort of wrap things up, I'm just going to real quick here just mention chemical bonds. And in the next video, you can take a look at some more details about chemical bonds. The bonds that we're mostly going to be interested in are covalent bonds, which are pairs of electrons shared between 2 atoms. We also have ionic bonds, which are electrostatic attractions between oppositely charged ions. And for our class here, this is what we are really interested in. We are interested in covalent bonds. And so in the next video, I will talk about how covalent bonds form and different ways that we can look at or represent covalent bonds. All right, so look forward to seeing you in the next video.